Okay, so 250 done. Let's do 251 now. Uniform cylinder, radius r, mass m, rotate freely about a stationary horizontal axis O, figure 1.59. Where's that figure? Alright, what about it? Okay, a thin cord of length L, mass m, wound to the cylinder in a single layer. Find the angular acceleration of the cylinder as a function of the length x of the hanging part of the cord. The wound part of the cord is supposed to have its center of gravity on the cylindrical axis. Okay, so this is x. Then you got this wound part, and then this wound part has this as center of mass. Fine. Wait, one second. What was that? I mean, even if it wasn't like that, we would just take the inertia, right? So, okay. Thin cord of length L, mass m is wound to the cylinder in a single layer. Find the angular acceleration of the cylinder as a function of the length. Oh, okay, right. So for the gravity part, right, for that you actually have to take, okay, yeah, the wound part of the cord is supposed to have its center of gravity on the cylindrical axis. Yeah, well, it does change, but like assume r is really small or something like that. Like it's wound a lot of times and r is really small. Does that make sense? Right. Let's do the thing then. So it's x down. What is the kinetic energy of this whole system? So you got, I mean, this is moving with velocity v, right? What is this guy's mass? It's like x lambda. So, but actually we do know what the mass was, right? So this is capital M, this is small m, right? It's of length L, we'll just assume. So lambda is just equal to m upon L. But really, what is this? It's just Lx is the mass, so half lambda x times v squared, okay, plus half I omega squared, right? And I think we could just, extend this because all of these points on this thread, they also have pretty much the same thing, right? Yeah, all have the same speed after all. So, you know what? Yeah, just say it's actually not this thing, but yeah, half lambda L x squared. That makes sense. Okay, so it's like half mv squared. I know. Sounds weird, but yes, that is the thing. So all these points are moving at the same speed, right? And that's why you can write like that. And then plus, so for this disk, you just need half of half. So you got 1/4 capital M V squared, right? Yeah, just as we do usually. Yeah, so that's awesome. You got that as a thing. Okay, and this energy, this would be basically what is imparted to the gravity. So how much of the mass went down, right? That's what you want to figure out. Right. Even though like it is x much down, we'll just say it's like x upon 2 down because center of mass. That makes sense. Should I even actually explain what's happening? No, I shouldn't. So it really is x upon 2 down. So previously all of this mass was, yeah, you will understand that by yourself. No big deal. You just want to integrate, it's linearly related to x, so it's like x squared upon 2 is the thing. Do I really have to explain this? Okay, so what is the mass of this guy? Just lambda x, which is now just say it's like x upon L times, just wait a second. Okay, this noise won't go away because even though my window is closed, this noise is still coming. So whatever. So x upon L times m. What is I doing once again? Yeah, the gravitational potential energy. So mgh, and it's supposed to be x upon 2, I think. Yes. Of course, that's how it's supposed to be. So assume r is really small or something like that. So then this is just going to be equal to mgx square upon 2l or something. And then next what we do is of course to differentiate and stuff. But actually, you know what? If you want to equate these, do this thing instead. Well, no, whatever. Just differentiate, right? So it's going to be what? So you got v dv and all that stuff. Really just like v times acceleration, and then you got this thing that is equal to, so when you differentiate this guy, it's just going to be like m g x upon, this is kind of weird because you got 2x over here, right? Yeah, okay, whatever. Just got L, and then takes upon it, which is v. So this cancels. Perfect. What does it say? What do you want to find once again? Sorry. Find the angular acceleration of the cylinder, right? Oh, so for they just need A. Yeah, you got the thing. So A is given by this thing, right? So you got 2m plus all that stuff. So like A is just equal to 2mgx upon L times of 2m plus capital M, all right? Now that we know this thing, we just want the angular acceleration. So this thing upon the radius. So you got 1 upon r and all that stuff. So there we go. This is going to be 2m upon, okay, first of all, just cancel all of this. 2m upon 2 capital M plus, oh sorry, 2 small m plus capital M. And you got this x upon L stuff, right? And then g upon r, right? This should be correct. Next question, 252. 52 is uniform sphere of mass m radius r rolls without sliding down an inclined plane set at an angle alpha to the horizontal. Find the measure of friction coefficient at which slipping is absent. All right. Oh, okay. And the kinetic energy of the system t seconds after the beginning of the motion. Okay. So it rolls down, right, without slipping. Then the friction cannot do any work in any case, right? So B is actually easy to figure out. So t seconds after the beginning of motion, yeah, sure. You can first of all just figure out the acceleration of center of mass. It's what a uniform sphere. So you got 2/3 mr squared plus mr squared. So you got like 5/3. Wait, no, it's not a hollow sphere. It's like a solid sphere. So 2/5. So it's gonna be 7/5 mr squared. That is the inertia. Uh, yeah, and what is the torque? The torque is, I mean, this is g sine theta, right? Of course. So like, yeah, mg sine theta, sine alpha, whatever. And then this thing times r, and then this thing times r. So that will actually give us the a value. So this cancels. You got 5 upon 7 g sine alpha as our acceleration. Sure. And what do you want? The kinetic energy system t seconds after the beginning of motion. Sure. So after that, you know what? Let's just figure out the angular velocity instead of this thing. So we'll just say figure out the alpha first, which we already did actually. So alpha is just this thing. Cool. And then you want t seconds, whatever. I could, okay, maybe you could think of it in a different way or something. Angular momentum conservation? Sure, actually that could work, you know. Yeah, that could. But no, let's not do that. It's gonna be complicated actually. You got velocity in that direction and whatever. And then V is equal to R alpha at least, sorry, R omega. At least that's the good thing. Ah, you could do angular momentum conservation, you know, right? But whatever, just figure out what angular velocity is after t time. So it's going to be 5 upon 7 g sine alpha upon r and that times of t, right? And then what you want is, of course, half I omega squared to get the kinetic energy. So 1 upon 2 I, for that you just need 7 upon 5 mr squared. And then you got omega squared. So this thing squared, right? So 25.49. And then you got g squared sine squared alpha upon r squared and then t squared. So some stuff cancels, just get, what is this? 5 upon 7, so you got 5 upon 14. This cancels, just got m squared, no, just m g squared sine squared alpha times t squared. Yeah, that's the thing. So that's part B. Actually, just leave alpha like that because, yeah, this is the thing. This is part B actually. So B done. Let's go to the first part. So what's the friction, right? Okay, you got the alpha value, but you can also do the same thing about the center of mass. So what forces are acting on center of mass? I mean, okay, there's this force, but that doesn't produce any torque. You just got the friction force. That is the only force actually. So this alpha is in fact equal to Fr upon, so like once again inertia, but about center of mass. You got, oh wait, am I doing this correctly or not? I think I am. So 2/5 of mr squared, right? Cool. So this cancels, just get this thing. Yeah. So you got 5f upon 2mr and that's equal to this thing. Cool. But okay, we'll do that later on. First of all, just figure this out. So what happens? This cancels. This cancels. F is just equal to 2 upon 7 mg sine alpha, right? So it's cancelled. But yeah, okay. But at the same time, we know that F is less than or equal to the normal force, which is just mg cosine alpha. And that is the question of friction, of course. So what does that mean? That just means that tan alpha, or this is 2.7 tan alpha is less than or equal to mu. So mu must be less than or equal to this thing. That's the minimum friction. So yeah, this is the minimum friction coefficient where this happens. It's just 2.7. So mu is bigger than or equal to 2.7 tan alpha, where no slip happens. Okay, next. 53. 53 is uniform cylinder of mass m and radius something starts descending at the 1.6, right? This thing, okay, start descending at the moment t equal to 0 due to gravity, neglecting the mass of the thread. Find the tension in tension of each thread and the angular acceleration of the cylinder. So the tensions will be equal, I guess. And the angular acceleration of the cylinder, okay. The time dependence of the instantaneous power delivered by the gravitational force. Yeah, okay. So it just starts falling down, and then what do you want to find? Then get the mass of the thread. Fine. Find the tension of each thread and the, oh, it's kind of, yeah, I get what's happening. Just that I don't want to do it. But whatever, just do the thing. So it's like the last question, but alpha is now pi upon 2 somehow. That makes sense, right? It's this disk. Okay, so mr squared upon 2, that's inertia, and then plus mr squared, like 3 upon 2 mr squared, 3 upon 2 mr squared. And what's the torque? The torque is gravity basically. So you got mg, no signal for anything, and that times r, of course. So that's our torque. Okay, torque upon inertia, just angular acceleration equal to this guy, and that's also equal to, so about the center of mass, which, yeah, about the center of mass, the torque would basically be just the tension force. And I'm using t, but actually it should be 2t. You know what? No, let's just use 2t, because why not? So you got 2t force in this direction, and then radius is just r. That's our torque upon inertia, just half mr squared. Perfect. Okay, so some stuff cancels out, but first of all, just simplify this thing. So you got that cancels, like g, okay, 2g upon 3r, I think. And that's equal to 4t upon mr, right? Yeah. And then just equates like t is equal to, that goes over there. It's like 2/3 of mg. Oh, you got that 4 over there as well. It's like 1 upon 6 mg. So mg upon 6. Cool. So the first part is done. That's the tension, right? So A is done. Yeah, okay. mg upon 6. Oh, where did it go? Mg upon 6, right? Okay. And the 2b in that case. So B is the time dependence of instantaneous power developed by the gravitational force, right? So for this complete system, yeah, this tension force doesn't do anything because this point of contact is it's stationary, right? So it's just the gravitational force that does everything, that does all the work, right? So the yeah, basically what you want to find is the work done by gravity at some certain t value. Actually, no, what you want to find is like F times V. So what is the velocity of the center of mass, and that times the gravity force. That's what you want to find. Cool. At some time t. So since we know what alpha is, it's doable in that case, right? And you know what? Alpha times r is just the acceleration. That's equal to 2g upon 3. So this times t is going to be the velocity or speed or whatever. So 2g upon 3 times t, right? And then this thing that you just want the rate. Do you actually want, no, you want instantaneous power, right? So that is exactly the rate. And then this times mg. So 2mg squared upon 3t. There we go. That's our other part. So 2mg upon, sorry, g squared upon 3 times t. Yeah, exactly. That's the time dependence. Next question. 254. 54 is thin threads are tightly bound on the ends of a uniform solid cylinder. So you got solid cylinder. Thin threads are tightly bound on the ends. Okay. The free ends of the thread are attached to ceiling. So something like this, right? The car starts going up with an acceleration. So the same case as this thing, but with upward acceleration omega naught of the ceiling, right? So this is actually with respect to ceiling, this is experiencing an extra force m times w naught, right? Okay, find the acceleration w dash cylinder relative to the car and the force F exerted by the cylinder on the ceiling. Okay, find the acceleration W dash of the cylinder related to the car. Okay, we can find that out. It was easy. So the second part, we use the acceleration, right, for the center of mass. Yeah, exactly. So this is actually very easy. It was just 2/3 mg. Sorry, 2/3 g. Yeah. And this is like 2/3 g effective. What's the big deal? It's just 2/3 of the gravitational acceleration plus W naught. No big deal, huh? And A, so what is the force F exerted by the cylinder on the ceiling through the threads, right? Yeah, so in the reference we just got this tension, but that's the same thing without the, okay, in the ground plane as well, right? Does that even matter? Doesn't. So yeah, what was the tension once again? It was mg upon 6. That was for one of these strings. The total would just be mg upon 3, but now it's actually mg effective upon 3. So m, and then you got g plus w naught. What am I doing? Nothing upon 3, I think. I think. Yeah, next question. 255. 55 is a spool with a thread wound on it is placed on an on an inclined smooth plane set at angle 30 degree to the horizontal. The free end of the thread is attached, just actually, okay. So a spool with thread wound on it. So you got two different radii. Okay. You got thread on it. It's placed on an incline. So 30-degree incline. And it's a smooth plane. Oh, that's important. It's actually a smooth, so there's no friction from this point. Fine. Angle 30 degrees to the horizontal. The free end of the thread is attached to the wall as shown. Oh, so 1.61. Perfect. Right. So free end is attached like this. The mass of the spool is given. Okay, m is just 0.2. Moment of inertia related to its own axis. So IC is God, why are they using these weird units? So it's 10 power negative 3, but then you got this thing. So it's 45 times 10 power negative 2. Sorry, negative 5. Yeah, that's right. And then the radius of the wound thread layer is 3 centimeter. So we'll just call it. Oh, so the wound, that's this thing, right? Okay. R is 3 times 10 power negative 2. All right. M just 0 0.2. Actually, 0 0.2 is good enough. No big deal. Find the acceleration of the small axis. Ooh. This is actually like, oh, the thing is, this doesn't have any friction. So even if this point is not stationary with respect to this guy, doesn't really change anything. Yeah, it's just rotating like that. No big deal. So cool. It's actually doable. No big deal, right? What's the what do you want? What find the acceleration of the spool axis? Yeah, no big deal. So you got g sine alpha or theta or whatever. Sine alpha. That's in this direction. Mg sine alpha, fine. And then that times R, that's the torque upon the inertia about this point, right? Yeah, which is, so it's mr squared upon 2. Wait a second. About this point. Hey, so this spool has what kind of mass distribution? What is the inertia about this point? Oh, we don't need that because you already gave us the inertia about the axis. So just do this plus mr squared. So you got I plus mr squared. Perfect. This is about angular acceleration. So this times r. There you go. You got the acceleration, the acceleration, right? So that's what you want to find, of course. Just calculate this thing. So m is 0 0.2, which is like 1.1 G is, assume it's 10. I know, wrong assumption, but whatever. And then you got sine alpha. It's 30 degrees, so it's got 1 upon 2. Then r squared. Okay, r is given to be, yeah, you should actually have small r squared, not this thing. But whatever, big deal. R squared, just r squared, not r squared squared. So, right, what we can do is just do I upon mr squared. So I upon r squared, right? Yeah. So you got mass, which is 0.2, just 1 upon 5 once again. Hey, that's weird. You know what? Just do it like this. g sine alpha upon I upon mr squared plus 1. So that's like 10 times 1 upon 2 upon what's I? I is this thing 45 times 10 power negative 2. Oh, so 10 power negative 5, I think. Okay, upon mr squared. So m is just 1 upon 5 and r is this thing. 10 power. Oh, you got 3 over there. So 3 times 10 power negative 2 and that thing plus 1 finally. Cool. 5 upon that goes up. First of all, it's just 15, so you got 75, then you got 10 power negative 3, I think, because that cancels. Yes, 5 by 75, sure. So it's like 5 upon 1.075. That's a bad value. Okay, maybe you wanna maybe just approximate this using the binomial theorem, right? Who cares? So it's like 5 times of 1 minus 0.075. I know it's cheating, but nobody cares really. Or you could actually do it the proper way. You could multiply by 4 on both sides and do the thing, but you know what? No. So this is like 5 minus 0 point is like 5, 2 carried on 35, 37, right? Okay. You got what 0.375 and then you just got 5.000. Right? So 5. What's this thing? 10 minus, sorry, 9 minus 7 is like 2, and then you got 6 and then point. So yeah, approximately this much, but I'm gonna say 5.5 because why not? 5.5 is better. Oh, actually it should be less than that, right? So it's like 4.6. Fine, 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 whatever. Just say it's 4.5. That should do it. So 0.5 comparison to 5, just 0.1. So cool, it's doable. It's not that bad actually. So there we go, 4.5 approximately. So first we'll just give them a formula and then we'll say the value. It's like this thing, which is approximately equal to 4.5. Do they want more precision? I don't think so. Why would they want more precision? Because this is like just torture calculation. I don't want that. Next question. 256. 56 is a uniform solid cylinder of mass m rests on two horizontal planks. The thread is, so no figure about. Oh, figure is given. It's like 1.62. Oh, this is different than the last one. Yes, it is. A uniform solid cylinder of mass m rests on two horizontal planks. A thread is wound on the cylinder. The hanging end of the thread is pulled vertically down with constant force F. Fine. Horizontal planks, but anything but the friction or whatever? No, nothing. Fine. Find the maximum magnitude of the force F, which still does not bring about any sliding of the cylinder. So, right, okay. If the coefficient of friction between the cylinder and the plank is equal to K, what is the acceleration W max of the axis of the cylinder rolling down the inclined plane? What? Inclined plane? Wait, am I going to some different thing? What is force? I don't know what this is. Uh, this is off the cylinder rolling down the inclined plane. There's no inclined plane. What are you talking about? It's not bring about any sliding of the cylinder. If the coefficient of friction between cylinder and planks is equal to K, so between this and that, fine. What is the acceleration W max of the axis of cylinder? Oh, this is weird. I don't know what it means. Down the incline. There's no incline. What are you talking about? Fine, I'll just do the first part and the second part I don't know what to do. Right. So an uniform solid cylinder of mass m rests on two horizontal planks. So thread is wound on cylinder. Right, whatever. Okay, find the maximum magnitude of the force which still does not bring about any sliding of the no big deal. This is the thing, right? So there we go. You got the normal force and you got gravity and okay, what is the normal force equal to? It's equal to F plus mg. All right. So our friction would just be mu times that critical condition, whatever. Right. First of all, just figure out the angular acceleration. So you got F times. So about this point where the contact is, what's the torque because of this guy? Just F times R, of course. The length. So arm is just R. So F times R upon inertia about that point, which is so it's a disk, right? like a disk. Mr squared upon 2 plus mr squared is just 3 upon 2 mr squared. And that's equal to, yeah, okay, so when you take the reference frame of the center of mass, what's the torque? So it's F times R, both in the same direction, in fact. So that's awesome. Yeah, but there's also another torque, which is because of the friction. So that's actually plus this thing, plus friction times R upon. So now the inertia is just 1 upon 2 mr squared. Perfect. Cancels. It's all of this just cancels. 3 over there. So what does that mean? That just means like, and this R cancels as well. So F is just F plus F is equal to, and by the way, I'm assuming F is in this direction, right? Okay, so F plus F is just equal to, what is this? Uh, yeah, well, it's negative 2/3. Sorry, it's equal to F upon 3. F is equal to negative 2/3 F. So my assumption was incorrect. It's actually in this direction. Whatever, pretty much the same stuff. So it's friction 2/3 F in this direction. That makes sense? Sure. And yeah, okay, so 2/3 F is just less than or equal to the normal force times coefficient, right? So mu n plus mu mg, sorry, mu f, what am I doing? Mu f plus mu mg, right? Exactly. That does it. There is some acceleration along this, well, whatever. We don't care about that, do we? No, we don't. What is the acceleration, the maximum acceleration of the cylinder rolling down the incline? What? Once again, this is a weird question. I don't know what incline plane they're talking about. It would just be like, okay, rolling on the plank, then what's the W max? In terms of what? So you got like, okay, W max. So what's our alpha and everything got this as the stuff. Right. So whenever your F is the maximum, that's when you have the biggest alpha. So that's when you have the maximum thing. Right. So what is the thing? Once again, our A would just be, or W or whatever you want to call it, 2F upon 3. And I think that's what they mean. Rolling on the plank, whatever. Just figure out what F is, right? And then you will have the thing. What is mu? Nothing is given to us. Let's solve this thing. F 2/3 minus mu is less than or equal to mu mg. So F can be only less than or equal to this upon that, which is like, okay, what's this thing? It's 3 mu upon 2 minus 3 mu mg. Perfect. And then A max, like, okay, F max is this thing, and A max is, so 2F upon 3m, so this 3 cancels, well, you can just see small m, doesn't really matter. And then it's like 2 mu upon 2 minus 3 mu, and that m cancels with g. Cool, that's our answer finally. Next question. Hopefully that's our answer. I don't know what they were wanting in the second one, but whatever. 257. 57 is, a spool with thread wound on it of mass m rests on a rough horizontal surface. Its moment of inertia related to its own axis is equal to gamma mr squared. Gamma is a numerical factor and r is the outside radius of the spool. Okay, so you got with thread wound on it. Okay, its own axis is given. Fine. Right, the radius of the wound thread layer is equal to wound thread layer is the outside radius of the spool. What do you mean by that? Of the wound thread layer. What? So it rests on a rough horizontal surface. Wait, is figure 1.63 for this thing? Oh, okay. The radius of the wound thread layer is equal to R. That's what you should say. Okay. The spool is pulled without sliding. So this is fine. Okay. Without sliding by the thread with a constant force F directed at an angle alpha to the horizontal. Without sliding. Okay. So this is rough surface or something? Rough horizontal surface. Cool. Okay. What? Find the projection of the acceleration vector of the spool axis. So it's in this direction actually. Kind of like that. I don't know. Actually, it's going to be in this direction, right? Because the torque is in Yeah, whatever. So what do you want? The acceleration vector of the spool on the x-axis. That's easy. Wait, there's also a y projection. How can there be a y projection? I mean, that vertical force, do we have to, what? The acceleration vector of the spool axis on the x-axis. That's just the x. That's just the acceleration. That's because there's no y component. Can there be a y component? Is f somehow bigger than mg? If it's bigger than mg, it's gonna go up. Then there's no normal force. It cannot have a normal force. But that would just mean it's, oh, it's case wise or something like that. The work performed by force F during the first t seconds of the uh okay beginning of motion. Right. It's very weird. I mean, okay, that's just gonna be the, because does gravity do any work? No. So just change the kinetic energy, of course. Right. So there's F in this direction. It's like the component of that is in this direction or whatever. Right. This guy's okay. It's moving with alpha angular acceleration like this about this guy. Or it's weird. It's really weird. We know it's gonna move like this, but it's okay. This thread, it must be taut all the time. So the amount of thread that loosens up, well, does it actually even loosen up? No, it's not. It's actually getting wound up. Wow, that's very weird. So when you pull it like that, if the friction is high enough, it's going to wound up. It's going to wind up your thread. That's weird, but okay, that's the way it works. Uh, Fine. Something's not right about this. The force is in this direction. You got that's like alpha. About this point, this is the arm, right? Huh. It's starting to not make sense actually. So you can figure out by geometry what this arm length is going to be and everything. I don't get how it cannot be in the x direction, it can also be in the y direction, something like that. Whatever, we'll just do it. Just do it right now. So you got this inner spindle, whatever. You got this outer radius capital R, fine. This is the line of action of the force F. You got this as the point. This complete thing is R. This is small r. This complete thing is capital R. Right? Yeah, it's making alpha with the horizontal. So this is alpha, right? Time is alpha. That's alpha over here. So that is alpha. So right. This is like, okay, sine of the, no. Cosine of this length is going to be r. So it's like this is equal to r secant alpha. Then this is capital R. So it's like r minus r secant alpha, right? And this is also going to be equal to alpha because parallel x. Yeah, okay, then that just means this times cosine alpha. So basically r cosine alpha minus r is the arm length. So the torque is basically just F times that. So, force is in this direction and then this is in that direction. So yeah, it is going in that way. That makes sense, I think. Yeah, sure. So it's just clockwise. That's why it's going to go in this direction. No big deal. Just do the thing. So F times this arm, r cosine alpha minus small r. Okay, all of that upon. So you got it all upon the inertia about what this point. You got what 3 upon 2 mr squared. Wait, no, okay, that's not right because it's not a disk. So you already know the inertia about center of mass, right? You got I plus mr squared. So like this thing, which is basically gamma plus 1 times mr squared. All right, cool. And that's our torque. This times r actually is going to be our acceleration. So what do you want first of all? The acceleration and the work performed by the force F during the first t. Just want the kinetic energy in that case. No big deal. We can do the thing. So yeah, the acceleration is just this guy. It's a constant, right? Of course it's constant. This cancels. Uh, F upon m times r cosine alpha minus r upon r. Yeah, and then also got gamma plus 1, so gamma plus 1 times r actually. That should do it. So that's our acceleration. Now, what do you want? Want the work done by F? Any other thing that can do any work? No, the friction cannot do any work. It's not slipping or anything. So that's the only work that can be done by this F force, right? Of course, no gravity. That it's not doing any work. Whatever. The changing kinetic energy. So, like, yeah, what's this thing? The velocity will just be a times t. So half mv squared, half mat squared, basically. So just this thing squared and then that times t. Why? That's just a lot of algebra. Okay, because you just got like f squared upon m, half f squared upon m, and then you got t squared and then all of this stuff squared. So r cosine alpha minus r upon gamma plus 1 r, all of that squared. Right, that's B. Next question. Next, let's go to 258. 58 is the arrangement shown in the figure 1.64 consists of two identical uniform solid cylinders, each of mass m, on which two light threads are wound symmetrically. Okay. Wait, what? 1.64. Fine. This. Okay. Two identical solid cylinders. Hmm. Right. Okay. Find the tension of each thread in the process of motion. Right. The friction up in the axle of the upper cylinder is assumed to be 0. So this is gonna move with V, and then right, these points are stationary. That much of thread is right. This point is actually not stationary. It is also moving with V. Oh, not nice. Not nice. I can't use energy conservation to get the thing done. That would be wrong. Need to think of something else. I mean, if this was just a mass or something, you would have done it like that, right? Yeah, you got velocity v in that direction. So with respect to the string, you can actually figure out. No, you can't. That would be wrong. Uh, wow, this is not. This is very weird, actually. I think there must be something I can do. Hey, you can use angular momentum conservation because look, the gravity forces they are acting on center of mass this guy, okay, and the center of mass of this guy. There's normal forces and everything, but about this point, the angular momentum is about this axis actually. Yeah, I mean it's symmetric and everything. So I already told you that I equal to omega, sorry, L equal to I omega works for radially symmetric surfaces and volumes. So you can still use that, and then about this point, you can just use L equal to I omega and then all that stuff to get the angular momentum. And yeah, okay, the change in that total angular momentum is actually 0 because the gravity forces on this, yeah, they don't create anything. That's awesome. So once you know what the velocity of this thing is, you can actually know what the velocity of that thing is. Hey, that's actually very nice. This is awesome, isn't it? Right, and once you know what the velocity of that guy is, you also know how the string is moving, and then you also know the velocity of that guy. So angular velocity, of course. So you would know with respect to this how that is moving. Of course. So let's do the thing. So at any given moment, suppose this has angular velocity omega, right? Then what's happening is that this point is moving down with omega r, but then that just means this point must also be moving down with omega r, right? It's a point on the string, whatever. This point is actually the point on the string, so not a point on the cylinder because more string is being generated, whatever, right? Does that make sense? Uh, sure, it should. And then with respect to this guy, because it's actually, it's not sliding on this thing. With respect to this guy, it's actually going. So it's like omega in that direction, and this must have omega in this direction at least. So with respect to this guy, it's actually omega r in that direction, right? So its own velocity, the center of mass velocity should be 2 omega r in this direction. Makes sense? Cool. Yeah, and in this way, you can actually get the thing. So, right. Forget about these strings and everything because now those are not important. They are massless anyway. right? That's equal to this. We got and once again, what is the dx upon dt? So if this thing is x, then what is dx upon dt? That just equal to, so first of all, it's omega r because of this guy, right? That much of string is being generated and everything. It's moving like that. Yeah. And then with respect to this guy, it's omega r. We know it's omega r in this direction, of course. This is weird. It's omega in that direction. With respect to this guy, your string is actually going like that. So that much of string is still being generated as seen by that guy, that guy's end actually. So basically, 2 omega r is equal to dx upon d, which makes sense, right? Which makes sense because this guy's velocity is 2 omega r, of course. So there we go. That is awesome. Right, now let's figure out the energy. So if the inertia is I, okay, what are these? These are cylinders, right? So you got mr squared upon 2, actually mr upon 4 times omega squared. That's for this guy. Okay, you know what? Yeah, let's just call this thing V because why not? So there we go. That's V. It's 2V in that direction. V just equal to omega r. So you can write this as mv squared upon 4. So mv squared upon 4 for this guy, and then rotational kinetic energy of this guy is just it's moving with, oh, it's also omega, right? So it's once again just mv squared upon 4, and then you got a translation kinetic energy, so like half m and then 2v squared, so 4v squared, right? Of course. So you got 2mv squared, I guess. So in total, you just got mv squared, and then you got 1 upon 2 plus 2. Cool. Right, that's our kinetic energy. The potential energy that lost is, right, so del u whatever, that just equal to mgx because this guy is having mass m and whatever, so mgx, and we know dx upon dt is equal to 2v. Okay, maybe we should not rush that. Fine, it's just mgx. Perfect, isn't it? Yeah. So each of mass m radius will just assume is r, and we don't actually even need that. That should work. So just differentiate and equate. So there we go. mv acceleration, that's 2, that's gonna cancel out, so like 1 plus 4, I think that's equal to, so differentiate this as like mgv basically, right? Because d upon dt is just, no, it's not v, it's 2v actually. That's gonna be 2v. Yeah, of course. And what do you want? First of all, find the tension in each thread in the process of motion. So for that, you basically just need the acceleration of this guy, right? Hey, so you know what? Okay, no big deal. We can just keep going. So v is the velocity of that point. I get it. We'll figure it out later. First, just figure out what our acceleration is. So a, which is, you know what? No, that's not right. It's just not right. I don't want this to be v. I instead want this to be v because in that way you can get the acceleration of this guy and you can actually get the tension, right? So we'll just say v is equal to dv upon, okay, dx upon dt. And then this whole stuff, I'm just going to put v upon 2 everywhere. So you're going to have v squared upon 4, right? Okay. And yeah, that's still mgx and everything. And now if you do the thing, and this cancels, we don't want all of this. Does that make sense? I think it does. So just differentiate and equate. So you got mv upon 2 times acceleration, you got 1 upon 2 plus 2 even now. So you know what? No, just write this 5. So 5 5 mv upon 4 acceleration, that is equal to, right, so you got mgx mg dx upon dt, which is mg times v. Now we can do that. Cool. This cancels. Now even though v is not equal to omega r, but it's still something that you can use. So right, the acceleration for this guy is basically just this thing, 4g upon 5, and this is just equal to g minus the tension, so the combined tension basically upon the mass of this guy, right? So T upon m is just equal to 1/5 of g. So the combined tension is just mg upon 5. So the individual tensions are just mg upon 10. There we go. You got the thing, mg upon 10. Next question. Isn't that awesome? 259. This is actually a nice method that I made. Yeah. Like otherwise you would actually have to do all that analysis and that would just be lot tough. Anyway, next question. 259. In the arrangement shown in figure 1.65, a weight A possesses M, okay, it's of mass M. Pulley P possesses mass capital M, also known as the moment of inertia I of the pulley related to its axis and radii of the pulley R and 2R. Okay, the mass of thread is negligible. What? Okay, fine. Right. Why is this? Okay, I thought it's given in italics. It's not. Find the acceleration of the weight A after system is set free. So after, right. Once again, you can just do that thing, right? Of course. So think about it. If this guy is actually going down with V, this must be going down with V upon 2, right? Yeah, and you just want what? Find acceleration of weight A. So that's why I'm going to use V for A. So A is going down with V. This guy's mass is just M, so half M V square. That's the kind of energy of A, and then plus. Right. So look, this is moving down with velocity what? V upon 2, and right, you got this, and then gonna go like that. Actually, fine. So you got half I, but not the I about center of mass. Instead, it's like I plus. This is 2R, right? Yeah, and oh wait, okay, that's R and that's 2. Okay, this is not right. If this is V, it's actually going to be V upon 3 because right, I mean this is the thing. Its central axis is like R away from the string, and then 2R away from that is this other thread, right? So if this is V downwards, then it should be V upon 3. Then okay, so I'm going to do that V upon 3 squared, whatever. But first of all, figure out the inertia. Okay, what is the omega for that thing? Is like V upon 3 upon R. So you can do that thing, V upon 3R. But first, figure out the inertia about this thread. Is that right? Yeah, of course. So I plus, it's like capital M, sorry. Capital M, and then you got R squared. Isn't that right? Yeah, this should work. And of course, it's like a square of that. So V squared upon 9R squared. That's our kinetic energy. So dk, that's just going to be equal to what? Or dk upon dt, whatever. That's what's that going to be? So 2 mvdv, all that stuff. Like, okay, va. Now you got m, and once again that gets off. Just got acceleration va is out. It is I plus mr squared upon 9 r squared, right? So it's like I upon 9r squared plus m upon 9. That should work. Okay, awesome. And this is just equal to du upon it or something like that. So yeah, or you could just say, well, the power due to the gravity, right? So now the thing is, it's not just this mass A that is having gravity acting on it, it's also this guy, right? So remember, this was actually moving down with V, and this was moving down. So like, okay, this, whatever this thing is, this mass, the center of mass, right? It was moving down with how much? V upon 3, right? So it's going to be V times of small mg, and this is going to be V upon 3 times capital Mg. Does that make sense? Right, that is the power, basically. Yeah, of course. So you got V times of, or let's say V times G times M plus M upon 3. That should do it. So there we go. This cancels. You got the acceleration. That's what you want to find, right? Acceleration of the weight A, and that's exactly this thing. No big deal. So multiply by 9 on both sides. You got 8 times 9m plus I upon r squared. I don't like it like that, but whatever. I upon r squared. I wish I could use I equal to gamma mr squared here as well, but no, I can't. And you got this thing plus m, yeah, that's equal to 3g times 3m plus m. Yeah, whatever, just do r squared stuff. So acceleration is just equal to 3g capital M plus 3 small m times r squared. I know. Upon, am I going correct? I'm of course going correct. What could go wrong? Okay, upon, so r squared and everything, divide by that. Just like I plus m plus 9m times r squared. Awesome. There we go. Next question. 260. A uniform solid cylinder A of mass m1 can freely rotate about a horizontal axis fixed to the motion, fixed to the mount B of mass m2, figure 1.66. So cylinder A of mass m1 can freely rotate about a uniform axis fixed to a mount B of mass m2. All right. A constant force F is applied to the end K of a light thread tightly bound on the cylinder. The friction between the mount and what is this? The supporting horizontal plane is assumed to be absent. Mount and oh, okay. There's no friction in this surface. Find the acceleration of the point K. This is force F. Fine. And the kinetic energy of the system. Okay. T seconds after. So this guy's center of mass is over here. That's a very big bonus. Okay. I mean, it's not moving. That's the thing. Okay. Kinetic system t seconds after the beginning of motion. So this guy's velocity, you can just easily figure that out. It's like F upon ma, and anything about the masses, they are using m1, m2. I'm gonna say maybe the mount is of mass capital M and this thing is of mass smaller. So that's our acceleration. So this times, what do you want once again? The acceleration of point K. Oh yeah, for that, first of all, you will have to all that stuff. Okay, that's the actual acceleration of, mount B. Okay, that's called AB, whatever. What is the omega for this? That is this force. We'll just ignore that. It's on the center. Doesn't matter. You got F times R upon the inertia. What is the inertia? What kind of shape was this thing? Solid cylinder A, right? Okay, cool. So mr squared upon 2. And then that times R for convenience. So 2F upon m is the relative acceleration of this point. And it's going in this, right, it's anti-clockwise. So that's perfect. It's just this thing plus that thing. So the actual acceleration is just F upon capital M plus small m plus 2F upon small m. Perfect. There we go. So A done. The acceleration of the point K, that is this guy. So F upon m plus m plus 2F upon small m. All right, what's B? It's weird. Okay, B is the kinetic energy of the system t seconds after the beginning of motion. So the only work you have is from the force F, right? Just figure out what the power of that thing. So it's the velocity in that direction, which we can just do, find that using this times t, right? Cool. Yeah, this point, you just say the thread, actually the thread itself, right? Because this point's velocity is the same thing as that velocity. This thread is at any point on the thread that's actually moving. So this K point, of course you could say that K is moving by this acceleration, so just this times t, call this A for now. So A times t, that is the velocity. Then this times the velocity by its, wait, what, sorry, velocity times the force, so this times F, that's the work being done, right? Okay, and what do you want? The kinetic system t seconds after the beginning. So just integrate this thing from 0 to t. We also need a dt actually. So that's the power, sorry, not the work. So 0 to t. There we go. That's the thing. So integrate this thing, get the thing done. You got f a upon 2t squared. Just put that in there. So like f times this, f t squared upon 2 times all of that. So you can just say f squared t squared upon 2, and then you got, yeah, actually even better. Take the 2 inside. So it's going to have 1 upon m plus 1 upon 2 times of capital M plus small m. Perfect, right? Next question. 261, right? A plank of mass m1 uh, with a uniform sphere of mass m2 placed on it rests on a smooth horizontal plane. Plank of mass m1, there's a uniform sphere of mass m2 placed on it. Okay, smooth horizontal plane. This is smooth. Nice. A constant force F is applied to the plank in what direction? Whatever direction. So got F in this direction. Fine. With what acceleration will the plank at the center of sphere move, provided there is no sliding between the plank and the sphere? So the sphere is actually gonna roll, and right, we got friction in this direction, whatever. Ooh, that's right. So with what accelerations? That's why, of course, because these two have different accelerations, right? Yeah, no big deal. We can still do it, right? So if this is moving with velocity v, hey, so okay, maybe just maybe conservation of angular momentum. Would that work? Maybe it would. Who knows? So yeah, I mean we know if you take like this point as so this point which is on the line of action of this force as our origin, then using conservation of angular momentum, like this guy's velocity doesn't matter at all because right, its angular momentum about itself is zero and about this point is also zero. Then the angular momentum of this thing should also be zero. What about gravity? Gravity doing anything? No. Friction is an internal force. It cannot do anything in any case. And there's no friction from this guy. So sure, you can just use concept of angular momentum and say that, okay, I mean, this thing has zero angular momentum. So, I mean, about this point, that is. Huh. We know actually it's going to move in this direction. So it's got some velocity in that direction. And then its angular velocity is like this. That's pointing in this direction. That's in this direction. Sure. So the inertia times omega, I know you might say that I already told you not to use this thing, but it's a radially symmetric case. You can do that, right? About this axis, it's radially symmetric. Okay, so I omega, that's this angular momentum in the clockwise sense. That's equal to the anti-clockwise sense angular momentum, which is like m times r times v. There we go. You got the velocity given the okay, something like that. Interesting. Uh, and then what? So once you have, and then you can actually figure out what inertia, right? It's just right. It's just 2/5. It's solid spheres, so 2/5 mr squared omega is just mrv. Hey, that's actually a nice thing. And what do you want once again? Maybe that's not the best way to be doing this because yeah, maybe that's not the best way. Ah, this guy's acceleration, it's f upon m1, right? Let's call this capital M. This Planck is of capital M. So it's F upon M1 is this acceleration. What about the acceleration of this point? So this guy's velocity is just V minus omega r, right? This guy's acceleration will be A minus alpha r. But we know what omega is, so we can actually write down what alpha is, right? First of all, just figure out omega. So this cancels, and just alpha r, of course. There we go. Omega r is just equal to 5 upon 2v. What do you want? Once again, the acceleration of the center of mass. So use v to represent everything. There we go. So our alpha r is just going to be 5 upon 2a. That's that. So a minus 5 upon 2a. What? That doesn't make any sense. Something's going wrong, isn't it? That's 2.5 for sure. And what went wrong exactly? What's happening? Something's going wrong, of course. Because how could this even happen? We know omega is in that direction. Oh, it's positive. What am I doing? It's v plus omega r. This is what we look for. So it's actually a plus 5 upon 2a. So yeah, 7 upon that looks awfully similar to something I've seen already. Whatever. So you got yeah. something is starting to not make sense suddenly. Well, whatever. So you got 7.2 v, but you could actually write it 7.2 v. So not acceleration, just velocity. This point is moving at 7.2 v. So what actually is going on is that this is moving at 7.2 v, and this guy's an acceleration, which is in this direction, which is a, right? That's what we thought. Okay, you could just say it's 7.2 a. It doesn't really change anything. So just do the force analysis. Like you got F is equal to m1 times 7 upon 2a, because no slip condition. That's why this thing. And plus m2 times a. That should work. And tada, you got acceleration. Right? Weird. I thought it would be different, but whatever. 7 upon 2a. Why did that happen? There must be some better way to do this, because it's not no it's no random number. It's important things. Pseudo acceleration, of course. So if your plank is going like this by acceleration a, assume it's actually don't assume that, but whatever. If it's going by a, uh, this point is not moving. With respect to the plank, this actually feels an acceleration. Okay, not acceleration, force. So force of ma in this direction, right? And then ma times r and all that stuff. Right? You just got ma, then r times of that, of course. Yeah, you want to find the acceleration, actual acceleration of the center of mass. So that r cancels. When mr squared, so 7/5 mr squared, but r squared is going to cancel anyway, so it's the thing. It's 5 upon 7a in this according to this guy, right? But then in actuality, what's happening is it's this thing minus a, so or a minus this thing, whatever. It's like 2/7 of a in that direction, which is exactly kind of the thing that we got. So that's why 7 upon 2 of this guy's acceleration is this acceleration. That makes sense? Yeah, that does it. So there was a much easier way of doing this. But now we have done this, like we know how to do it. So this guy's moving with a, this is going to move with 7 upon 2a, right? Okay, so just figure out the accelerations. This is the thing. Uh, yeah, and did they give any values? No, they didn't. Right, just solve this thing. So a is equal to f upon, you say 2f upon 7m1 plus 2m2, right? There we go. And then, right, this is the acceleration of the sphere. Acceleration of the plank will be 7 upon 2 of this, like 7f upon 7m1 plus 2m. Cool. Next question. Sometimes energy is not the best way. Sometimes you got to do actual, you know, motion analysis. Okay, 200 and what? 62. Let's do the thing. Uniform solid cylinder of mass m r is set in rotation without, sorry, about its axis with an angular velocity omega naught, then lowered with its lateral surface onto the horizontal plane and released. Okay, the coefficient of friction between cylinder and the plank is equal to k. Fine. How long the cylinder? I think we did this somewhere. I can't remember where, but whatever. So how long the cylinder will move while, wait, what? With sliding, right? Okay. And the total work performed by the sliding friction force acting on the cylinder. Okay. What total work performed by the sliding friction force against, sorry, acting on the cylinder, right? Okay, this is a, how long will it move with sliding? Was there, okay, maybe think about it. Is there some easier way to do this than actually doing everything for, I don't think there is. I don't think there is. Just find omega as a function of t and v as a function of t, and it needs to be equal to omega r, right? That's gonna give you the time. Yeah, what else? Wonderful work performed by the sliding friction force acting on the cylinder. Okay. Hey, there's one thing. So for B, you can just do angular momentum conservation and get the thing done actually. Of course. So just doing angular momentum conservation, you will actually get the thing done. Hey, and at every given moment, you can do the thing, right? Yeah, sure. That's not going to actually give us the time though, because, right, that's an unfortunate fact that it will not give us the time. That's not nice. For time, you actually have to do the thing. So for time, let's do the thing, right? So what's alpha and what's A? So constant of friction is K, right? Normal force just mg times K. Just say mu, sorry, right? Okay, that times of R upon inertia, right? Of course, about the center of mass. So it's a uniform solid cylinder. It's just a mr squared upon 2, so 1 upon 2 mass. That's our alpha. Alpha is equal to this guy. Mhm. And initially it was not having any v, right? So it's just like omega whatever, and then you got friction that's decreasing this, but it's also like increasing v. So the acceleration, right? This is the deceleration, angular deceleration, and this is the actual acceleration for velocity, right? What is our alpha or negative alpha, whatever? That is 2 mu then g upon r. Cool. And our a is, so it's like mu g, just mu g, right? So mu mg upon m. Cool, that's the thing. So you got A and you got alpha, right? Cool. Now what? Yeah, just figure out V and omega. So V is mu g times t, and omega is oh, and by the way, this is in that direction, it's in this direction. So eventually, right? Okay, these are actually aligning themselves, right? Cool. So it's just omega naught minus this guy, minus 2 mu g upon r times t. So what you want is, of course, v equal to omega r. So for that to happen, mu gt is equal to omega naught r minus 2 mu gt. So t is just equal to omega naught r upon 3 mu g. That's when this will happen. So first guy, we got the answer. A is just this thing, omega naught r upon 3 mu g, right? Now for the second guy, what I'm thinking is, what if, think about like angular momentum, right? That's conserved because friction forces along the, yeah, we could do that. And yeah, I think that's a way of doing it, of course. And then in the end, what's happening is that like that point is stationary. So, right, that angular momentum about that point and then just shift and something like that. Sure, it's gonna work out. We can do it, right? Okay, so let's not do all of this. Instead, just want a total work performed, right? That's going to be the loss in kinetic energy, I think. There we go. Let's just figure out what the final kinetic energy should be. Who am I kidding? Why am I doing this when I already have the solution? Just put this in there and get the omega value. Why even? No, no, I won't. I'll do it from scratch. Okay, so initially kinetic energy initial, that's just equal to what? Your angular momentum is, or whatever that thing is, it just has omega whatever. Yeah, it's like half I omega squared. And this is, let's just do this for all kinds of bodies. So half I omega naught squared. And kinetic energy final, which is equal to what? Half I plus mr squared times omega. But yeah, that's one way. But you could also do it like this thing. You could just do L squared upon 2 inertia about that point, right? Yeah, because, yeah, I mean, it's hard to explain, but I am doing it in my head. you need to do it as well. And then actually you could just well, whatever. And what is angular momentum? It stays constant, is I omega naught. And this is IC, by the way. And actually this I is different. This is the inertia about that contact point. So I plus mr squared, right? Okay. So you got K final, you got K initial, cool. And just put L equal to this thing in there. So it's going to be IC squared, I squared basically, times omega naught squared. So delta K is, so K final is K initial, or just loss of kinetic energy. Just negative delta K is what we find. This thing minus that thing. So I upon 2, I just plug out that omega naught squared as well. Okay, so you got 1 minus I upon I plus mr squared, right? So this is just I upon 2 omega naught squared, and then you got what? Mr squared upon, what am I writing? Mr squared upon I plus mr squared, right? And suppose your I is of the form gamma mr squared, then that's even better because you can just write it like this thing. This will actually be equal to, we'll just write I omega naught squared upon 2 in fact, and then you can write this thing as, 1 upon gamma plus 1, right? Or if you really want, you can write like this thing, gamma upon 2 times of gamma plus 1 times m r squared omega naught squared. Cool. So there we go, that's our answer, I guess. So B, it will always be this thing, actually negative of that, right? So it's negative gamma upon 2 times of gamma plus. You know what? I'm going to keep this notation. So gamma will be that numerical coefficient all the time. Because I think some forms they are better expressed in gamma instead of actually inertia. So in this particular case, gamma is what? 1 upon 2? This is going to be equal to what? You got 1 upon 10, you got 3 upon 2. So it's negative 1 upon 6. So negative 1 upon 6 mr squared omega naught squared. Cool. That should be the thing, hopefully. Next question. So 263. I don't think we have enough time because maybe I'm just running out of time. What is the time right now? It's 1:21. Yeah, I spent more than what I had to. So that's it. I'll see you in the next video. Bye.